pleasure to have Rajesh Ganapathy with us for this Infosys seminar. Rajesh did his PhD with Ajay, and then he had a postdoc in Cornell, and for last several years he is a faculty member at James Bangalore. So Rajesh works broadly in the area of soft matter, and that's what we will hear from Rajesh today. You also had a small stint in industry, isn't it?
Before my PhD, yes, for a year, yes. Okay. All right, thanks. It's a pleasure to be here. Thank Pratap for this opportunity. So what I really have to tell you today is about two stories. And I'll be happy to just, I'm in no hurry to get to the second one. So if I just end with the first one, and please do feel free to stop me as and when needed. So the two stories are basically the stuff that we've been doing with glasses. And the second one is basically on driven amorphous solids, and the system being bubbles such as these. And before I go any further, I'll just tell you a little bit about what is it that we do in our lab. So these are the two topics that I'm going to be talking about. This is something that we recently started doing, which is on looking at micro heat engines. The idea is that you replace the Avogadro number of molecules that you have in the cylinder, which you compress by a piston, by a single colloidal particle that's being held in an optical trap. Now, since you have just one particle doing the work for you, you're going to be dominated by fluctuations. And the idea is, can the principles of thermodynamics also explain the working of this sort of an engine? So we look at particles of weird shapes. Okay, so these are ellipsoids, these are rods in a shear flow. We can make particles that look like trimers, tetramers, and more complex colloids. The idea is, what happens when you start playing with particle shape? How does it influence flow? How does it influence crystallization, glass transition, so on and so forth? We're also looking at, at some time ago, we looked at defects in colloidal crystals. And so this is basically a grain boundary that's being sheared. It's a three-dimensional polycrystal in which we are shearing a grain boundary. And you can basically look at what happens to the grain boundary at the level of a single particle. Right? And we've also made some forays into self-assembly, trying to grow crystal structures, so on and so forth. But there's one unifying theme, which is that we would like to see what's going on. So the typical scale bars of all of these images, so each particle here is about a micron. These are bubbles that are millimeter sized. So the idea is, by just looking at phenomena, you have a better feeling for what's going on. All right? And today I'm going to be telling you about this. And just to indulge you for a little bit, we don't even understand glasses in flat space. But that shouldn't prevent us from throwing them on curved space and asking what happens to glasses. Okay, so this is a movie of basically binary, so the particles of two different sizes on the surface of a droplet. Okay, and we're trying to see if the physics, whatever little we know on flat space, and how does it differ when you put in curvature. All right, okay. So what's the glass transition problem? Okay, so you start with the liquid, okay, and you cool it rapidly enough so that you bypass crystallization. You enter what's called you enter the supercooled regime, in which the liquid is metastable. Okay, but there is no way, if I were to give you a metastable liquid, there's no way you can actually tell whether this is metastable or not, because any function, any 2-point correlation that you look at is going to be identical to that of a liquid. All right, so this is really an equilibrium phase. You can't tell until a crystal nucleus forms and the system immediately forms a crystal. So you have this metastable liquid and you cool it further down. At some point, what's going to happen is that the time scale over which molecular relaxation happens is going to be so much more slower than the time scale over which you observe the phenomenon, which means eventually you're going to fall out of equilibrium and you enter this glassy state. All right, and depending upon how fast you cool, you basically can play with this glass transition temperature over a suitable window. All right, and yes.
But we often say, for example, supercooling of water, when you cool it very slowly, isn't it? Means do you rapidly?
Yes, so you need to rapidly quench. So the idea is that you don't give the liquid enough time to form a nucleus.
And what will happen to the
So, okay, so the trouble with superheating is that what intervenes is that you always have a free surface. So you're never able to superheat the crystal until you maintain a boundary condition which prevents the system from melting. So you need to really cool fast you need to basically suppress the formation of a nucleus, because in this regime, the crystal is the stable thermodynamic state. So in this you don't have a free surface. So when you're talking about the melting of a crystal, so if you have a crystal that's confined on all sides by another stable configuration which is crystalline, you can start superheating and then you end up with a different sort of melting process as opposed to the conventional melting where you have a free surface. So you don't have the pre-melting effects kicking in, so we suppress the boundary. Okay, so the fascinating thing about the glass problem is that a whole variety of materials, starting from metals to polymeric glasses, amber is like a classical example, and even active systems. Okay, you take aggregates of living cells, bacteria, and you take them at suitably high enough densities, and they show all the features that you would see in these sort of systems. Okay, so there is a goal to understand why this sort of a universal picture kicks in, and understand what is the fundamental basis for this formation of a glass. And today what I'll do is to just focus on colloids. And I'm sure everybody here knows about it, but basically you're talking about small particles in a fluid, and you can see these particles move around in real time so that you get to put your optical microscope and track the dynamics of every single particle. And by tuning the volume fraction, which is basically just the number of particles per unit volume, you get all these various phases. Okay, you can get a liquid phase, you get a crystal phase, and somewhere in between you do have a glassy phase. Okay, and in all my experiments, to basically suppress the formation of a crystal, we're going to take particles of two different sizes, okay, so that you suppress the nucleation of a crystal, all right? Now, instead of looking at the plot in which I just showed you the enthalpy as a function of temperature, if you were to look at, say, the relaxation time or the viscosity scaled by the glass transition temperature, so this temperature versus viscosity or relaxation time, what you see is that, so this is for a whole bunch of different glass formers. Okay, and what you see is that over a very narrow window near TG, you basically see the shooting up of relaxation times by about 12 orders of magnitude. All right, and empirically, you just define when the relaxation time of the system reaches about 100 seconds, you call it the glass. Okay, and now there are materials that fall under two different categories. One is basically materials that just follow an Arrhenius relationship. Okay, so you give the system a little, your KT is getting further and further smaller, so you just do not break bonds, so you find a simple sort of relationship. But what's interesting is that if you look at this branch, okay, so there's a log linear scale. So if you look at this branch, you basically have the activation energy changing as you approach this, and these are called as fragile glass formers. Okay, you don't have a simple Arrhenius scaling. You have the slope of this curve changing constantly, so you have the activation energy changing. And the only way you can reconcile this change in activation energy is if you assume that more and more particles come together to basically relax the liquid. All right.
How do you measure the relaxation time scales here? There are lots of different dots on that line.
Yes.
Are they all same measurements?
So you could do you could do neutron scattering or light scattering. You could do dielectric spectroscopy. Any of those measurements will allow you to look at the relaxation times. So I really don't know what was used for each of these measurements, but basically the goal is to just tell you that there are two classes. One in which the activation energy doesn't change. You have a simple Arrhenius sort of slowing down. One in which the activation energy changes, which means there's some sort of cooperativity.
Certainly some different parameter depending on the experiment. So what was that experimental variable that looked at?
So one thing that you could look at is density correlations. So how does it decay? So what happens is in this regime, when you're very far away from the glass, you get a simple exponential decay. But as you start approaching the glassy state, you see a plateau, and the plateau immediately doesn't die down, and that is some sort of a measure for what a glass would mean. Okay. Okay, so, but what's fascinating, okay, is that you see you have this enormous growth in relaxation times, and people experience with critical phenomena would immediately think that we should go look for some sort of a growing length scale in the problem, which explains why the slowing down happens, all right? And when you go look at the length scale, so this is the structure factor for glycerol right across the glass transition temperature at 160 Kelvin, it shows no obvious change, okay? So you have this enormous growth in relaxation times and you can't pick out anything in your 2-point correlation. So this is a density correlation, so you don't see anything in 2-point correlations, okay? But then now I'm going to show you a video, okay, in which,
so these measurements,
yes, this one,
yeah,
yes.
the time scale is much shorter than the relaxation, so that it proves almost static.
Yes. These are quasi-static measurements, so that, yes, so that nothing is evolving in the system as a, and one more thing, you don't have time in, so you're just looking at an instantaneous snapshot. So all you're looking at is how are the molecules arranged in space. You have no information whatsoever about time, but then the goal is in fact to look for some sort of a static order, which you don't seem to be finding.
Yeah, but what I mean is that to take any measurement, there is a finite time involved.
Yes. Oh, in that time scale, you assume that things are not changing. Yes. Okay. So what I'm going to show you now is a movie. Okay. So this is a spectacular experiment that was done by the Wade's group at Harvard, and so what you're seeing here is basically colloidal particles in a 3D volume, and the particles are color coded in terms of their mobilities. Okay, a particle that doesn't move much is basically shown as a blue dot. A particle that moves quite a bit is shown as a red sphere. Okay, and now what you find is that you see in a dense liquid. No, these are the same. These are the same type of particles, but color coded in terms of how much they move. Yes, after you collect, say, hours of data, you can basically track every particle and you can find out how much they've displaced. All right, and what you see, I forgot to put in what volume fraction this was, but it's pretty close to the glass transition. And what you find is that, no surprise, that in a dense fluid, if you have to move, you have to displace a whole bunch of particles around you. Okay, so you see that a particle that moves is in the vicinity of many other particles that also moved quite a bit. Okay, so these are basically what are called as dynamical heterogeneities. And what you do find is that you can associate a length scale of these heterogeneities. And what you do find is that as you start cooling the liquid, as you start approaching the glass transition temperature, this length scale grows. But it is purely a dynamical length scale because you're looking at mobilities, you're not looking at static order. All right? And now, so people who believe that the glass transition phenomenon is purely a kinetic mechanism get very excited because there is no static order and you have a dynamical quantity that's growing, okay? And there is even a theory called as dynamical facilitation that basically explains this rapid growth in relaxation times, okay? And you see that according to this theory, you will find that the relaxation time tau diverges only at t equal to 0. It's a purely kinetic phenomenon, okay? So all of this is nice, but then this relaxation time data can also be fit equally well, I'm sorry about the colors, by what's called as a Vogel-Fulcher-Taman relationship, okay? And here, the relaxation time seems to diverge at a finite value t naught. It's not t equal to 0, it's t equal to t naught, okay? And I will tell you why this t naught is interesting in a little bit, all right? So now instead of looking at dynamics, let us say that I look at thermodynamics. And what I'm going to be measuring is basically the specific heat capacity at constant pressure. Okay, so this is the liquid. I bypass crystallization, I continue to cool the liquid, and I finally reach, I'm in this branch. And when I reach the glassy state at Tg, the specific heat capacity is going to drop. The thing to note is you see it drops roughly to the crystal value. It drops to the crystal value because the rattled room available for particles in a crystal and the rattled room available for particles in a glass are not very different. Okay, so the heat capacity roughly drops to the same value. Okay, and I'm sorry about this. And this is for ethyl benzene, which is a fragile glass former, which means your activation energy is constantly changing as you approach the glass transition temperature.
So these you're saying that you are particularly the...
Yes, so this is the liquid branch. I'm sorry about this. I think I'm pressing more than one. It goes into glass at this point.
Yeah, but
yes.
it would have in principle also gone to a crystal.
In principle could have gone, yes, in principle could have gone to a crystal, but across this entire curve, you're maintaining the cooling rates so large that you never let the crystal form. You never let the nucleus form. Because once you form the nucleus, it's going to be immediately a first order transition that's going to go to the crystal state. It's going to be a pretty run.
Looking at this curve, how can I tell that it is not that first order transition? I need some other input like scattering.
No, so in this heat capacity itself, all you see is a jump, right?
Yeah.
Yes, right? So I'll just show you one other measurement, so which you can decipher from this curve. And
there is a small difference between the two.
There's a small difference, yes.
But then if I go slightly lower in temperature, there is almost no difference.
So the thing is, you see, the trouble with this measurement is you're allowed to measure the heat capacity only up to this point. Because if you don't let the system explore phase space, what is the validity of even measuring the heat capacity? Because so this is...
Experimentalist view of heat capacity. I put some heat, measure the change in temperature.
Sure. So, which is why it closely follows the crystal curve. In the sense, but it is a non-equilibrium measurement because you have not let the sample relax. You have not let the sample explore phase space. So this jump that you see, you're not sure that if you were to cool it even faster, whether you have gotten the same jump at this point in T. You would have gotten it much later or much sooner, which is what differs from a first order transition. In the sense that it will always happen at the same temperature. Yeah.
Even then, water will go through a first structure at some other temperature, not necessarily at 0 degrees centigrade, depends upon how much it cools.
The first order transition?
Fast, yeah, because if you do it fast, then because first
No.
order transition takes you time.
If you give it enough time to nucleate,
I'm not giving it enough.
then you're supercooling.